Hello, my name is Anaqi Afendi, and my summer research at the LMSE lab has centered around computational protein design. I will present a Gaussian process regressor-based machine learning model for phosphatase activity prediction. The working model I made can be found on GitHub. The aim of my research was to develop a machine learning model that when fed a protein sequence for a given substrate, would be able to predict what that protein activity would be, Vmax if you will. The machine learning model I will be presenting today uses a Gaussian process regressor approach to perform this prediction. The significance of this research is such that it will allow for the faster identification of viable protein sequences. Typically, researchers will spend months performing high throughput screening, sampling on almost every variable in a theoretically infinite search space, when trying to identify and optimize designer proteins. The average hit rate on these tests is very low, at about 2 to 3%, and out of those, fewer still actually outperform the current standard. With this current machine learning model, researchers will be able to identify viable protein sequences in a shorter amount of time using a targeted and constrained search space. These proteins have many applications, ranging from drug discovery and pharmaceuticals to use of sustainable technologies such as bioreactors to the production of fermented foods. As I mentioned earlier, my model uses a Gaussian process regressor, GPR. A GPR is a multidimensional regressor method which allows for curve fitting. As you can see from this diagram, the solid green line represents the mean of the observations, while the gray represents a 2 standard deviation uncertainty around the curve. Essentially, a GPR produces entire families of curves where there exists a nearly infinite combination of curves who all exist within a certain margin of error. As you can see from this blue line, we can then obtain predictions using this model of what the output would be on an unseen, untested input. The probability density function of the fitness of the sequence can be seen by this red line, and it is normally distributed. The GPR allows us to focus and constrain our search space on regions which have a higher probability of yielding more desirable proteins. The shape of the curve is determined by a covariance function, also known as a kernel function, whose shape is in turn governed by a set of hyperparameters. For the purpose of this investigation, I had settled on the Matern kernel, as this is what is most commonly used in literature. During times like this, we were not able to access the lab to conduct experiments ourselves, so we had to source our data elsewhere. We used protein sequences and protein activity data from a paper which had investigated the haloalkanoic acid dehalogenase HAD superfamily. HAD are a superfamily of phosphatase proteins. The paper tested 218 phosphatase proteins on 168 different substrates to measure their activities. The first diagram illustrates a map of the substrate library that was used on this test plate. The second image is the activity data of just one protein on these substrates. I used a Python script to scrape the data and the sequence data from NCBI and UniProt protein databases. Having a large data set like this to train and test the machine learning model is key to making a good machine learning model. It is first important to understand what makes up a phosphatase protein sequence before we can attempt to model off of it. As you can see from this diagram, the researchers from the aforementioned paper have color-coded 3 main sections of the phosphatase protein sequence. The blue region is the main section of the phosphatase protein sequence. The blue region is the surrounding helices. The purple region represents the cap domain, and the orange region is the core Rossmann fold. It is this core Rossmann fold which is of most interest, as this is the active catalytic site of the protein. The Rossmann fold in particular is what allows the protein to bind to nucleotides, such as the organophosphates from the substrate library. We want our machine learning model to be able to extract and learn these features, structures, and their roles, and in fact, maybe learn new and other features that us humans cannot identify. The core Rossmann fold might be the main binding site. However, the rest of the protein structure still significantly determines what the activity of the protein would be like. It would be nice if our model can learn how these structures are all related and what role they ultimately play in determining the activity of the protein. However, with this limited dataset, a lot of hand engineering and specialist insight may be required still to develop a competent model. Before we can train and test our model, there are a few important data encoding and preparation steps we have to perform. As you can see from this histogram of the protein sequence length, most of the sequences were shorter than 300 amino acids in length. And so we had to cut out the sequences shorter than 300 amino acids in length so that we can cut out the sequences that were too long. When we trained and tested our model with these long sequences, it performed poorly as it was not able to generalize well. Next, we performed a sequence alignment step on the protein sequences using Clustal Omega, which is the current state-of-the-art protein sequence alignment software and methodology. This sequence alignment step is important as it allows for two things. Firstly, the aligned sequences are all the same length, and this makes it easy to feed into the model, which requires all input data to be the same length. Secondly, the aligned sequences are easier for the machine learning model to identify features from and group trends of amino acids within the sequence that it can attribute to the resulting activity. Lastly, we performed the encoding step. We chose one-hot encoding as this is the encoding method of choice as it allows for the simple conversion of the protein sequence into a numerical matrix format. This step is crucial as the machine learning model cannot perform logic on strings. It can only process them numerically. I will briefly explain how the method of one-hot encoding works. If we have a given data set of two sequences, we can start by encoding just the first sequence. Firstly, we perform a padding step as the second longest sequence in the step. Using the dash symbol to fill in spaces so that all the sequences are as long as the longest sequence. This step is already done by Clustal in our case. Secondly, we couple the padded sequence with an amino acid lookup table and perform numerical indexing on the values each IUPAC amino acid was assigned. Lastly, we perform a vectorization step, and this represents each entry in the sequence as a column vector of zeros and a 1 in the row corresponding to the indexed amino acid. In order to measure the performance of our model without having to collect more data, we came up with a way to perform a train test loop using the same data set. Firstly, we randomly shuffled the data set. Next, we split the data 80% into a training set and 20% into a test set. Then we feed the training data into a GPR hyperparameter optimizer, which optimizes the hyperparameters on a kernel function to the training set. These optimized hyperparameters are fed into a regressor prediction model, along with the protein sequence X, if you will, from the test set, and a prediction of the protein activity, Y. We can then compare the predicted activity of the test set to the real activity. This is plotted in the diagram below for the substrate L-arabidol 5-phosphate, and we measure the performance of this model on the substrate using the correlation coefficient R. This split train test loop was performed 20 times for each substrate for efficacy of the results. This final experiment took me about 6 hours to run across all of the substrates. As you can see from the diagram below, out of the 168 substrate models made, the model was somewhat reliable on 19 of the substrates and had a decent prediction on 16 of them, while the remaining 133 substrates had almost no correlation between the predicted and measured activities. When developing future models, we aim to improve our model prediction and performance up the line and into the green zone, of course, of both good model prediction and consistent prediction. This low R value of 0.4 was chosen as this allows us to better gauge the abilities of the model during development. Additionally, if we compare this model to protein experts, it is arguable that this model outperforms any expert, as no one can really say, just from looking at a protein sequence, what its activity on a given substrate would be. The poor overall performance of the model can be attributed to mainly a few factors. Firstly, we only tested with the Matern kernel so far, but there do exist other kernels which could provide better results. Secondly, GPR is not the best model for sequential data, as it is a simple model, and when trained on such high-dimensional data, it does not generalize on unseen data very well. Lastly, the data set we have is quite small when compared to the length of the sequences we have. It is not adequate. Hence, more hand engineering and thus more layers should be used in this model. In this case, we only used one. In the future, we will explore GPUCB, which is a Gaussian process model which performs unconstrained bandit setting to provide a better recommendations with minimal regret. And we will also consider adding more layers, such as one-dimensional, two-dimensional convolutional layers, and testing other methods of encoding, such as natural language processing, which will improve the models. This will also allow us to add feature extraction methods, if you will, into our model. Despite the not so stellar performance of the model, this project was successful in determining a baseline machine learning model to perform some feature extraction and prediction capabilities. I would like to thank Professor Krishna Mahadevan for providing me with the opportunity to work in his lab, Paul Zhu for allowing me to work on this project with him and for being a great mentor, Kaushik Raj for helping me with this project and also being a great mentor, and Chester Pham for assisting me with this project.
So thank you, Anaqi, for your presentation. Now I would like to address the judges and ask if you have any questions. Can you please unmute and ask them? Thank you.
I guess it seems, can you hear me all right?
Yep.
Yeah, Jason here, nice presentation. Yeah, it does seem like for this kind of problem where you have, like, your amino acids almost form an alphabet and your proteins can all be of different lengths. So that is kind of like more, generating sequences of words, or and that's often done with like recurrent neural networks. So has there, does it make more sense to pursue that path rather than, this Gaussian curve fitting?
Yeah, actually, that is the main idea and flow that we're moving towards.
Yeah.
A lot of the work that I had done this summer was to generate this as a baseline to show this is not the best way to do things.
Okay.
And I spent a long time like learning about neural networks and how they work.
How many different amino acids are there? Like, how big is that alphabet? How many, if I think of it like an alphabet, yeah.
There's about 20. Technically 21 if you include the blank spaces with the dashes but there are other amino acids that some proteins have. They're unique, but they're not the standard IUPAC, and we're kind of like constraining the scope to the IUPAC.
Got it. Thanks.
Do we have time for another question?
Yeah, go ahead.
Yeah, Anaqi, it's Professor Bussman. So I don't know nearly as much about this as Professor Anderson might have, but so I'm going to ask you kind of maybe a bigger picture question. You were generous enough at the end to say that this didn't work as well as perhaps you would have hoped, but and then you gave us a couple of reasons for that. But can you just briefly explain to someone who doesn't know a lot about machine learning and whatnot how, for example, the choice of a kernel could affect your results? In other words, you chose one, and then at the end you suggested that there are others you could try. But how does one choose one intelligently to generate a good result from the get-go?
That's actually a really good question. So that's a question that I've been investigating for a while, and one of the best ways, and I guess you can like argue that this leans towards looking for decisions that support your hypothesis, but generally the way people would do it is by testing a bunch of different ones on this data that they have, and whichever seems to look the best. And look the best means it would fit what they would expect it to do. But
right.
In something like this, in most cases, absolutely you wouldn't know what to expect, because we're trying to see trends that we wouldn't be able to see.
Right.
Because if they are trends, yeah. And usually people would look at literature and see what people previously have done, but I think the best way to go about it is to try many different sets, but to try to cross different sets of data with it from the same distribution, of course, and see which one fits that distribution the most. It would probably be harder to use that to see out of trend data and see out of trend proteins, which there definitely exist a lot of out of trend proteins, but we just wouldn't be able to model that for now.
Okay, so